This is the beginning of video 4 for section 4.6 on related rates. We're starting on number 16. Number 16 says we have a sand pile that's sand is falling from a conveyor belt at a rate of 10 meters cubed per minute. And so the volume of this dV dt is changing at a rate of 10 cubic meters per minute. And it's forming a cone shape. And it says the height of the pile, so let's write this down, the height of the pile is always equal to 3/8 of the diameter. Okay. And I now want to see what we can do. It wants to find, let's see, how fast are the height and the radius changing when the pile is 4 meters high. So I need to write a volume equation. So volume of a cone is pi r squared times h. So if I take the derivative right now, I'm going to get a dr dt and a dh dt. I'm looking for, let's start with part A, I'm looking for dh dt. dh dt. So what that means, I need to turn my r into h's. So I go over here and I look at this, and I have diameter, which is unfortunate because I want radius. So how much is a diameter? I know that a diameter is twice the radius. So diameter is actually equal to 2r. So I could rewrite my height equation to be 3/8 times d, or 3/8 times 2r, which would reduce the 2 and the 8 to make 4. So I think I should know that the height is 3/4 of a radius. Alright, and so then with that information I can now convert and say volume equals pi r squared times 3/4 r, where volume equals 3/4 pi r cubed. And it occurs to me that I'm actually about to answer part B, because it wants to know about the radius. So this is actually going to be part B, and that's going to be finding dr dt. Alright, so finding the derivative would be dv dt equals 3/4 pi is all constant, so we have a constant multiple rule. So the 3 comes down, making it 9/4 pi r squared times dr dt. dv dt is 10. The radius at this time we don't know, but it does tell me that the height, says do all this when the height of the pile is 4 meters. So if height is 4 meters, then I should be able to find out what radius is by doing some simple math. And the radius would equal 16/3. So I get 9/4 times 16/3. That's my radius. And I am squaring it times dr dt, which is what I'm looking for. Okay, so I could do some reducing here, but eventually we are going to need to go to our calculator, I think, because I've got 2 16s and 2 3s. And actually this is kind of nice. The 2 3s, so the 3 squared is 9, so that 3, which is actually a 9, cancels out that 9. And then I'm left with 16 squared divided by 4, which is 64. So I have 10 dr dt, or dr dt equals 10 divided by 64, which is 0.15625. And that would be units of meters per minute. Okay, so now I got to find dH/dt. So with that, there's two ways I could do this. One, which I think would be a little more complicated, is I could just go back to my original equation and now switch this around and make it r is equal to 4/3 of an h. Plug that back in. I'll only have h's in my equation this time instead of r's like last time, and then I can repeat the process. But I should also, if all I want to know is dH/dt, then I'm looking for an equation that has h in it and other stuff that I know. And if we come over to this equation that we use to convert, notice it relates h and r. So I should be able to take the derivative of this equation, dH dt equals 3/4 of a dr dt. I'm looking for dH dt, so all I need to know is dr dt, and I just found it. So I should be able to write that dH dt is equal to 3 times, let's see, my answer, divided by 4. So I get an answer of, and I hope these are right, 0.117 meters per minute. And that should be the right answer. Again, if that's a little bit weird for you, then don't worry about it. Go back to the original equation and replace the correct variable, leaving yourself only h's, so replace r, and then see if you get the same answer. Okay, so 17 is going to be a pretty similar question. We've got another cone, but this time it is a conical reservoir, and it's pointing down, and water is draining out of the basin at 50. So we have 50 meters cubed per minute, and it's draining out. So it's going to be a negative rate because the volume of which we're finding the rate of change of, so dV dt, is getting smaller. The volume is getting less. The base radius is 45, and the height is 6. So it's a very wide, shallow reservoir. And just like the earlier question, as the water level is changing in here, it's conforming to the shape of the cone, and we know that that would make similar cones, and again the ratio of their sides would be equal. So that means if I look at the height to the radius of any of the cones that we're forming, that'll equal the same rate, or the same ratio I should say, as the height to the radius. And so now I have in front of me a conversion equation that I can use if I need to relate an h to an r, or vice versa. Okay, so 17a says, how fast is the water level rising when the water is 5 meters deep? Alright, so when the water is 5 meters deep, how is the water level rising? So this is changing, so we're going to call this h, we're going to call this r. So they want to know about how fast is the water level falling. So they're asking me about dH dt. So we need a way to relate volume and height, and obviously that's going to include the volume of a cone, 1/3 pi r squared h. If I take the derivative right now, I'm going to get a dr dt and a dh dt, and I don't have enough information to answer that question. So I need to convert my variables, and I'll use this statement. I want dh dt, so I need h's left in the problem. So I need this to say r equals. So r equals, looks like 45/6 of an h. Multiply by r on both sides, multiply by the reciprocal to get rid of 6/45, and we're right. So that means volume is equal to 1/3 pi 45/6 h squared times h. So volume equals nothing good, h cubed. So let's see, let's do that. It's 45 times 45 divided by 6 squared, so that's 36. And then let's divide it by 3, because I've got that constant there. And it looks like I got 18.75 pi h cubed. So volume equals 56.25 pi, so 3 came down, left with h squared, times dh dt. So now I just need to plug in what I know and solve for what I don't. Wait a minute, dv dt, not just v. So I know dv dt is negative 50. I've got 56.25 times pi. H is, at this moment in time, 5. So 5 squared is 25. And so what's that going to give me? Negative 50 divided by 25 is negative 2. So I get negative 2 divided by 56.25 divided by pi. So it looks like I get an answer of dh dt equals negative 0.10113. And that would be in, let's see, what units are we in? Meters. Meters per minute. So according to this information, it's not draining, it's not lowering the height at a very quick pace at that time. Okay, let's see what we got left. Number 20, we're inflating a balloon. So we have a sphere. The balloon is being inflated at a rate of 100 pi feet cubed per minute. I wrote that right up here earlier. So what is that a measure of? That is a measure of the volume of the balloon. So dv dt should equal that number. And part A says, how fast is the balloon's radius increasing at the instant that the radius is 5? So it's inflating, and we're going to look at how fast the volume is changing when the radius is 5. So I'm looking for dr dt. How fast is the radius changing? Okay. So we need to relate those. So hopefully we realize we need the volume of a sphere. And the volume of a sphere, is 4/3 pi r cubed. I take the derivative, I only have 2 variables, it works out. So I get dv dt equals 3 comes down, cancels with that 3, 4 pi r squared dr dt. Plug in what I know. I know the radius, they told me, is 5 feet, and solve, and I'm done. I'll let you do that. Part B says, okay, do it again, but how's the surface area changing? Well, the area of a sphere is simply 4 pi r squared. familiar from before. So dA dt would be, the 2 comes down, 8 pi r dr dt. And then I plug in and solve. And I'll leave that for you to do. Alright, and now we get to the last question I have on this sheet here. I realize there's a few more left to go. Number 21. And this one says we're bringing in a boat. We're pulling it into the dock by pulling on this rope. The rope is represented by this blue line, which then continues, like if I'm over here pulling on it. So the blue line, the rope is coming this way. So it's being pulled. The dock is 6 feet up. The rope is being hauled in at a rate of 2 feet per second. So we need to label something as 2 feet per second. And what would that be? I'm pulling on the rope at that rate, so the blue line is coming in at that rate. So we haven't labeled this. I'm just going to label it Z, just because we had a hypotenuse of Z in our example problem in class. So I'm going to say that dz dt, the rate of change of Z is 2 feet per second. But notice Z is getting smaller, so we need to remember it's actually negative 2 feet per second. Alright. How fast is the boat approaching the dock? So part A. How fast is the boat approaching the dock at a certain time? So if we label this X, because this is changing, Z is changing, the only thing that isn't is 6. I have now a relationship, because they want to know about dx dt. So again, Pythagorean theorem works out pretty well. I get z squared equals x squared. And I can go ahead and plug in the 6, because the 6 is not changing, it's static. So now when I take the derivative, I get 2z dz dt equals 2x dx dt plus the rate of change of that constant we're referring to, which is obviously nothing. So now I can plug in, I know dz dt, I'm looking for dx dt. I plug in z, I plug in x. Do I know both of those? So it says, how fast is the boat approaching the dock when 10 feet of rope is out? So at this moment in time, this is 10. And so a little bit of Pythagorean action tells us we actually have a 3, 4, 5 triangle doubled. So this is going to be 8. So now we have enough information, you can solve that. Part B now asks us about how is theta changing. So we just need to write an equation that relates theta to something else we know. We just found out information about x. We know information about z already. So I'm thinking I want to use the constant 6 and the z only, just because I haven't actually even found my answer to part A, which will be the dx dt. So I'm going to relate theta, z, and 6. And I think the easiest way to do that is with cosine. So I've got cosine of theta equals adjacent over hypotenuse. It's possible it might have made more sense. In fact, let's just go ahead and fix it. Instead of doing cosine, because I don't like my z in the bottom, and I don't want to have to z to the negative 2 power or whatever. It's no big deal. You can certainly do it. But since cosine cut the z in the bottom, I'm going to actually do the inverse of cosine, which is secant. So secant of theta, it would be z over 6. Now the derivative of secant theta is secant theta tangent theta equals, d theta dt d theta dt, which would equal 1/6 of a dz dt. So now I just need to know I don't really need to know theta so much, but I really need to know is what is secant of theta. So secant is going to be the reciprocal of cosine, which is going to be 10 over 6th times tangent of theta. Tangent of theta is going to be 8/6 times d theta dt, which I don't know, equals 1/6 of -2. And then that should find me d theta dt. Alright, I'm going to stop this video at 20 minutes and pick it up with one more video to finish this 4.6.